Dear students, today we can discuss about quantum theory and photoelectric effect. We know there are different theories about the nature of light. First we have Newton's corpuscular theory, and then we have the Christian Huygens wave theory. Then lastly we have the quantum theory. So each theory was developed to explain new physical phenomena. So with the help of the Christian Huygens wave theory, the phenomena like diffraction, interference, also the reflection and refraction can explain. But there was a new phenomena, photoelectric effect, that cannot be explained by the Christian Huygens wave theory. So in the situation, in 1901, Max Planck put forward a new theory of light called quantum theory. So with the help of this quantum theory, we can explain the photoelectric effect. So according to this theory, light is radiated in the form of tiny packets of energy. Each packet is called a quantum or a photon. Since it is an energy packet, we can have an expression for the energy of the photon. Suppose if nu is the frequency of the photon, then its energy is given by E is equal to h nu. Here h is a universal constant called Planck's constant. Its value is 6.63 into 10 raised to negative 34 joule second. We can also express the energy in terms of the wavelength. Here, if c is the velocity of light, the wavelength of lambda is related to the frequency nu by the expression c is equal to nu lambda. Then energy can be expressed as E is equal to h nu, that can be expressed as h into c by lambda. So let us substitute the values. Then we can have the expression of energy E is equal to 6.63 into 10 raised to negative 34 into 3 into 10 raised to 8 divided by lambda. After the calculation, we can have energy of the photon can be expressed in joule, that is 1.989 into 10 raised to negative 25 by lambda joule. Usually, we are expressing the wavelength of light in nanometers. For example, the wavelength range of the light, visible light, is from 400 nanometer to 800 nanometer. So if we express the wavelength of light in nanometer, what is 1 nanometer? 1 nanometer is equal to 10 raised to negative 9 meter. When lambda is expressed in nanometers, the energy of the quantum can be rewrite as E is equal to 1.989 into 10 raised to negative 16 divided by lambda, provided lambda is expressed in nanometer. So this is the expression for the energy of the photon when lambda is in nanometer. Then we can have the another unit for the energy, that is the electron volt. It is the energy gained by an electron when it is accelerating through a potential difference of 1 volt. So the relation between the joule and the electron volt. 1 electron volt is equal to 1.6 into 10 raised to negative 19 joule. Even though it is not an SI unit of energy, many of scientists think that it is a convenient unit to represent very small amount of energy encountered in particle physics. Then we can also express the energy of the photon in terms of electron volt. So for that, we can divide the expression for the energy in joule by the energy corresponding to 1 electron volt. So that is the E is equal to 1.989 into 10 raised to negative 16 divided by lambda, all divided by the energy equivalent to 1 electron volt, that is all divided by 1.6 into 10 raised to negative 19. So we can have the energy in terms of electron volt, that is after the calculation we can have that is 1204.3 by lambda electron volt. We should note that here lambda is expressed in nanometer. So in nanometer, when lambda is expressed in nanometer, we can have the energy of the photon in terms of electron volt as E is equal to 1243 by lambda. Now this is some fundamental ideas in quantum theory. Now we are moving to the new phenomena, that is photoelectric effect. So when light is incident on certain metals like sodium, potassium, rubidium, cesium, it is found that the electrons are emitted from the metal surface. And these alkali metals shows the first photoelectric effect. So that is the emission of electrons from a surface when irradiated by light. Not only these alkali metals, other metals like iron and copper also shows the photoelectric effect. But here the light is not a visible light, but we have to irradiate these metals ultraviolet rays or X-rays to remove the electrons from the surface. Now let us see. This is a picture showing the photoelectric effect. Here the light is incident on the metal surface. So here the electrons are ejected from the surface, and these electrons are called photoelectrons. Now let's have an experiment showing the different factors affecting the photoelectric effect. Here we can see an experimental arrangement. Here there is an evacuated glass chamber. Here there is an evacuated glass chamber in which a silver plate that is coated with cesium and another metal plate that are placed inside the evacuated glass chamber. Here the material which is made up of this chamber is quartz. The particularity of quartz is it is transparent to UV as well as the visible light. And here you can see these two metal plates are connected to a battery externally. Here on the left side you can see the plate which is connected to the negative terminal of the battery. It is acting as a cathode, and the terminal and this metal plate on the right side which is connected to the positive terminal of the battery is act as a anode. And a galvanometer or an ammeter is included in the circuit for the detection of current. Now these are the experimental arrangement, and also there is a voltmeter is there to measure the potential difference. And here, when the light falls on the cathode, what happens? The electrons are ejected from the surface of the cesium. Since this anode is placed at a positive potential, the electrons are attracted towards this anode, and this flow of electrons from the cathode towards the anode constitutes an electric current, and the current flows through the external circuit, and the galvanometer or the ammeter shows a diffraction. That is the experiment. Now we can see a small animation which explains the photoelectric effect. Now we are going to see what are the different laws of photoelectric effect. Here we have another scientist, Millikan. He conducted a number of experiments and he arrived at some following laws. That is known as the laws of photoelectric effect. Please remember the previous figure. This experimental setup. Here where the light is incident. So for the incoming light there is a frequency and there is a wavelength. And there is also a intensity. Intensity means is the number of photons per unit area, incident per unit area. And the electrons are emitted, they are called photoelectrons. When they constitute a current, that current is called a photoelectric current. Now, let us see what are the important laws of photoelectric effect. Here, so let us start with the experiment with the visible light, which have the lowest frequency. Keeping the intensity remains constant, and then we increase when we start with the experiment with the low frequency, we can see that there is no photoelectrons are emitted. That means there is no deflection in the galvanometer. So as we increase the frequency of the incident light, we can see at a particular frequency onwards, the photoelectrons are emitted, and that we can be detected in the galvanometer. That means there is a particular frequency below which there is no photoelectric effect. That minimum frequency that is required for the photoelectric effect is called the threshold frequency. So there is a minimum frequency required for the light to initiate the photoelectric effect. So the photoelectric effect happens only when the incident light has a minimum frequency or the the threshold frequency. So below the threshold frequency, even though the light has a very high intensity, there is no photoelectric effect. If the incident light has the minimum frequency, then with the low intensity or with the low intensity of light, there is a photoelectric effect. So for starting the photoelectric effect, the intensity of light doesn't have any role. Only condition is that the light should have a minimum frequency called the threshold frequency. Correspondingly, we can also have a threshold wavelength. The threshold wavelength can be defined as the maximum or the largest wavelength above which there will not be the liberation of photoelectrons from a metal. Because we know lambda is equal to C by nu. Okay. Usually we are representing the threshold frequency as nu zero. Okay. So if nu zero is the threshold frequency, then threshold wavelength lambda zero can be expressed as lambda C by nu zero. So from this we can see that the photoelectric effect is frequency dependent. It is the frequency dependent. Next, once the photoelectric effect starts, then the intensity has some role. After the photoelectric effect happens, when the intensity of light increases, then we can say there is adding the photoelectric current. Because when the intensity of light increases or decreases, that means the number of photons incident on the metal surface per unit area is increasing or decreasing. So each photon has capable of liberating one electron from an atom. Then as the number of photons are increasing in a given area, that means the more number of photoelectrons are emitting. Okay, that means the photoelectric current, that depends on the intensity of light. Okay, so the intensity of light affects the number of ejected electrons, that is the photoelectrons. That is greater the intensity, the larger will be the photoelectric current. One condition is that the frequency of the incident light always greater than the threshold value. So the second law is the intensity of light affects only the number of ejected electrons, that is the photoelectric current. And the third one is, you can see, as the incident light incident on the metal surface, at that moment the electrons are emitted. That means there is no time lagging between the incident of the light and the emission of photoelectrons. That is, the photoelectric effect is a instantaneous phenomena. The photoelectric effect is an instantaneous phenomena. There is no time lag between the incidence of radiation and the emission of electrons. Now, the photoelectric effect is well explained by the world-renowned scientist Albert Einstein. He explained the photoelectric effect using the Planck's quantum theory. As we know, according to the quantum theory, the light consists of small packets of energy called a quantum or photon. If you use the frequency of a photon, its energy is equal to h nu. Here h is the Planck's constant. And when a photon is incident on a metal surface, its energy is used up for the two purposes. The first one, the important one is the some part of energy of the incident photon is utilized to liberate the electrons. As we know, the electrons are bound to the nucleus. So to eject or to liberate an electron from the metal surface, we have to given some extra energy. So the major part of energy of the photon is utilized to release the electrons from the metal surface. This corresponding energy is called, the energy required to this purpose is called photoelectric work function. Photoelectric work function. Usually it is represented by the symbol phi. So some part of energy is utilized for the work function. What happened to the remaining part of energy? The remaining part of the energy of the photon is given as the kinetic energy of the liberated electron. Okay. So if m is the mass of the electron and v is the velocity of electron, then the kinetic energy of the electron is given by E is equal to half mv square. Then the Einstein's photoelectric equation, that can be expressed as the energy of the incident photon equal to the sum of the two parts of energy. That is, E is equal to, here E is equal to h nu. H nu is equal to 5 plus half mv square. H nu is equal to 5 plus half mv square. Phi is the work function, and half mv square is the kinetic energy of the electron. So this is the Einstein's photoelectric equation. Here the work function is a constant for a given material. Okay, so it is different for the different material. For a particular material, it is a constant. Now let us think about what will happen when we decrease the energy of the incident photon. Suppose there is a photoelectric effect is taking place. Here the electrons are ejected and they are moving to the anode plate with some amount of kinetic energy. Okay, so when we try to decrease the frequency of the incident photon, what will happen? First of all, the kinetic energy of the electron will be reduced. So in the h nu equal to 5 plus half mv square, the half mv square part will be reduced. Then we still decrease the frequency. We are going to decrease and decrease. What will happen? So the amount of the incident energy is just enough for giving the work function. That means the kinetic energy of the electron become 0, because the incident photon energy is just enough, just sufficient to give the work function. That means here the photoelectrons are just liberated from the surface without any kinetic energy. That means just the photoelectric effect taking place. So that frequency is called, in the last part we are seeing that minimum frequency required for the photoelectric effect is called is a threshold frequency. And here when we decreasing the frequency, and again we decrease and we are reaching to the threshold frequency. At the threshold frequency, the incident photon energy is fully utilized for it is just sufficient for the required work function. So in that case we can express h nu 0 is equal to phi. Okay, as we know, the frequency nu 0, it is the frequency at which the kinetic energy of the electron becomes 0. So we can express h nu 0 equal to phi. So instead of phi, we can substitute h nu 0 in the Einstein's photoelectric equation. Then the h nu is equal to h nu 0. Instead of phi, we can have h nu 0. So h nu is equal to, that is the incident photon energy, is equal to the work function, that is h nu 0 plus half mv square. Okay. Now in terms of the wavelength, we can express, as we know, nu is equal to c by lambda. nu 0 is equal to c by lambda 0, then the expression becomes h into c by lambda equals h into c by lambda 0 plus half m square. Lambda 0 is the threshold wavelength. Okay. Now let us find an expression for the maximum velocity of the photoelectron. We have the Einstein's photoelectric equation, that is h nu is equal to h nu 0 plus half m square. So we can combine the h nu 0 coming to the left side, then we have half m square equal to h nu minus h nu 0. Here h is the common, so h into nu minus nu 0. From that equation we can have v is equal to square root of 2h into n nu minus nu 0 all divided by m. Okay. Suppose instead of frequency, we can express the energy of the photon and the work function as the incident energy can be expressed as we can replace h nu by E, and h nu 0, that is the work function, can be replaced by phi. Then the expression of the maximum velocity of the photoelectrons becomes square root of v is equal to square root of 2 into E minus phi all divided by m. Now let us see the applications of the photoelectric effect. One of the main application of the photoelectric effect, that is the photoelectric cell. So what is a photoelectric cell? Photoelectric cell is a device that is used for converting light energy into electrical energy, employing the photoelectric effect. Here, there are three types of photoelectric cells. One is the photoemissive cell. Photoemissive cell, that is based on the fact that just the electrons are emitted from a metal like cesium when it is exposed to light. That is simply a photoelectric cell. So it is just utilizing the photoelectric effect. That is, when the light is incident on such a cells, the electrons are emitted. Then the next type of cell is the photoelectric cell is the photovoltaic cell. Here, the photovoltaic cell is based on the fact that it is like a direct converter of light energy into electrical energy. Here, the source of EMF, the external source of EMF, is not utilized for the working of this kind of cell. Here, it generates EMF without the application of any external potential difference. So usually in the photoemissive cell, that is, we can move to the previous figure. Here we have a source of EMF, which are keeping this cathode C as the negative potential, and this metal plate is keeping as the positive potential. So, but in the case of the photovoltaic cell, without a source of EMF, the cell generating the EMF, that is, it is generating the electrical energy, or it convert the light into electrical energy. That is, it employs the photoelectric effect in semiconductor materials like selenium and gallium arsenide. Okay. So such semiconductors, without the help of the external source of EMF, we can generate the electrical energy. So this kind of photovoltaic cells are exclusively used in solar cells. That is, you can see in the calculators and in some watches. They are using this kind of photovoltaic cell. Then the third type of cell is the photoconductive cell. So in the photoconductive cell, it is utilizing the materials like the semiconducting materials like cadmium sulfide. Here, when light falls on this kind of materials, semiconductors, the electrons are emitted and resulting in a very large increase in their conductivity. So the materials like cadmium sulfide, when the light is incident, the electrons are emitted. So due to the particular nature of the cadmium sulfide, when the light is incident, all on a sudden, a large number of photoelectrons are emitting, resulting there is a large decrease in the resistance of the material and hence increase in their conductivity. So that is the name called a photoconductive cell. So these photoconductive cell are mainly used as the photoresistors. And these photovoltaic cell, and they can be used as a source of electricity to power the electronic equipments. Now let us see some of the applications of photoelectric effect. There are numerous applications. Here, just some of them are just enumerated. It can be used as an illumination meter. That is, illuminating powers of light sources can be compared using a photovoltaic photometer. So now it is called a photometer. Okay, so we can compare the illumination capacity of the different sources of light. And a burglar's alarm, and that can be constructed with a photoelectric cell. Here, in front of the door, we are placing a photoelectric cell and an IR transmitter, and it is continuously transmitting IR radiations, and it is received by the photoelectric cell, and there is a particular value of photoelectric current. So if somebody try to open the door or somebody try to cross that position, what will happen? There is a breaking of IR radiations. So there is a breaking of photoelectric current. So that is detected. That is sensed by some other electronic equipments, and it produces the alarm. Okay. That is also the case with the fire alarm. In the fire alarm, we are using the IR radiations. Here also we are using the IR radiations. Fire means that is a heat. Okay, heat means it is the IR radiations. So we have the photoelectric cell, which are more responsive to the IR radiations. So when the such a photoelectric cells are continuously receiving the IR radiations and producing some kind of photoelectric current, when there is a fire is caught, what happens? As the fire increases, there is a IR radiations are increasing. So the photoelectric cell, the photo current also increases. If it exceeds a particular value of the current, then alarm will be sound. Okay, that is the fire alarm, and they are also used for in some relay circuit, and it is very efficient detector of IR radiations. So it is used to detect the ships and aircraft, because the lead selenide cells, they are a very high efficient detector of infrared radiations. So they are used for detecting the ships and aircraft by the radiations given out from their exhaust. So that is detected by this kind of the photoelectric cells, like the lead selenium cells, and if the photoelectric effect exceeds a particular value, so they can assume that some ships or aircraft are passing nearby. And the photoelectric cells are used to reproduce sound recorded in a talkie film. And also an array of photoelectric cells that are used in television cameras for the conversion of light signals into electric signals. And that we have already mentioned, a photovoltaic cell can be used as a solar battery. And also we are using the photoelectric cell for making the street lights on and off automatically according to the level of daylight. And also it is used for controlling the temperature of a furnace by detecting the IR radiations. So we have a numerous applications, and here we are just mentioned some of them are, and you can go through the a large number of applications of the photoelectric cells, photoelectric effect.